Good morning, dear students. In today's class, we'll see the solution of homogeneous partial differential equation involving derivatives with respect to one independent variable. See, we have seen in the previous class the same examples, but you can find here. So it is a function of z, and we have the same variable. Means the same here also z, and here same variables are there. Then such kind of equations are going to called as what here homogeneous. And in the previous class we have see the differential equation. Here also we have differential equation, but here function this derivative is function of z, but here the variables are x and y, non-homogeneous. So such kind of equations are going to call non-homogeneous, but way of proceeding same, but a small change in this example and in this example. So these examples already we have completed in the previous class. In today's class we'll see. So solve dou square z upon dou x square plus z equal to 0, given that when x is equal to 0, z is e raised to y, and when x is equal to 0, dou z by dou x is equal to 1. These are the conditions, and we need to apply. So it is same as how we have done previous classes examples. Now the given differential equation, if the function and the variable are same, so we need to convert this in terms of our ordinary differential equation form. Means this dou by dou x you convert in terms of d by dx form. So here dou square z upon dou x square is there, so it will be converted in terms of d square z upon dx square plus z. So this can be written as d square z plus z equal to 0, or you take z common, so left what inside here, d square plus 1. So from this you can see the right hand side is equal to 0, means this is not of any kind of type here. So this is for only we'll get complementary function. So auxiliary equation is d square plus 1 equal to 0, or this can be found like that, and this is nothing but root of the given differential equation, so which is nothing but complex, free from real part, only real imaginary part is there. So which can be written as zc. Instead of y we are taking z, because this is the equation in terms of z. So therefore we have to take complementary function of z is equal to c1 cos x plus c2 sin x. But we have to replace c1 as f of y and c2 as g of y, and this zc you consider as a z, and because here no particular integral, so zc is nothing but a general solution or complete solution. So therefore by replacing c1 as fy and c2 as gy, we can say that it is a complete solution with f of y and g of y. So the solution is z is equal to f of y. Instead of c1 I had taken here f of y cos x, plus instead of c2 I had taken g of y sin x. Give equation number 1. Now go back to the condition. They have given when x is equal to 0, z is e raised to y. So apply these values in equation number 1. So when x is 0, you replace wherever x is there, you replace 0, and z is equal to e raised to y. So z is equal to e raised to y means here replace z as e raised to y is equal to f of y as it is, cos of 0 because x is there, in place of x 0, plus g of y as it is, sin of 0. So on simplification, e raised to y as it is, f of y, cos of 0 is 1 into f of y is f of y, but sin of 0 is 0, that's why 0 into g of y is 0. So therefore we got the value of f of y is equal to e raised to y. So keep this one as it is. Now with the second condition, when x is equal to 0, dou z by dou x is equal to 1. But in the equation number 1 we don't have dou z by dou x. So before applying this condition value, we need to differentiate equation number 1 partially with respect to x. See I had done here. So this z is nothing but it will become dou z by dou x. F of y is a constant. Partial derivative of cos x is nothing but what here, minus times sin x, plus g of y is a constant, keep as it is. Partial derivative of sin x with respect to x partial is nothing but what here, it is cos x. So simplify, or else you can apply these conditions directly here. So dou z by dou x is nothing but 1 minus f of y as it is, x is 0, that is sine of 0, plus g of y as it is, cos of 0, because x is 0. So on simplification, sine 0 is 0, 0 into anything is 0, 1 as it is. So cos of 0 is 1 into g of y is g of y. So on simplification, g of y is 1. So substitute f of y and g of y in your equation number 1. So replace this f of y as e raised to y and g of y as 1. So we'll get a required equation as z is equal to e raised to y cos x plus sin x. So in this way we need to simplify for partial differential equation of homogeneous. Okay. So the next example is, next question is, solve dou square z upon dou x square is equal to a square z, given that x is equal to 0, z is equal to 0, and dou z by dou x is equal to a sin y. So when x is 0, z will become 0. When x is 0, the second condition will apply. So the given partial differential equation of homogeneous, because function z and here also z is there. So same function with the same variable we can consider as a homogeneous. So take this a square z inside, and we know that this is a homogeneous differential equation by seeing that. So we have z here also z, no xy term, so that's why it is a homogeneous. So this can be written as in the ordinary differential equation form, that is d square z upon dx square is equal to minus a square. So simplify and get the auxiliary equation, and from the auxiliary equation get the root. Root is what here, plus or minus a, that is d is equal to plus a and d is equal to minus a. Write the complementary function, because here a function of z means it will be zc is equal to c1 e raised to ax plus c2 e raised to minus ax. So the solution of PDE is nothing but z is equal to c1 e raised to ax plus c2 e raised to ax, but you have to replace c1 as f of y. Why f of y only? Because this is this partial differential equation is what here, with respect to x means we have to take opposite as y. F of y we are considering this one, and c2 is equal to g of y. So in place of c1 you write f of y, in place of c2 you write g of y, and say it is a equation number 1. So here by using the conditions we'll find the value of f of y and g of y, and we'll replace it, which is nothing but the required equation of the given partial differential equation. Now applying the first condition, when x is 0, z is 0, equation 1 becomes 0 is equal to, that is the value of z here, z is equal to, replace z is 0, f of y into e raised to x into 0 is the, replace x is equal to 0 means e raised to 0, g of y into e raised to 0. So e raised to 0 is 1, so therefore it will become f of y and g of y. So this equation I will rewrite is as f of y plus g of y is equal to 0, and give equation number 2. Now apply equation number condition number 2, x is equal to 0, dou z upon dou x is equal to a times sin y. But we know it is in the form of equation z, so we need to differentiate this equation number 1 with respect to x what here partially. So it will become dou z by dou x is equal to f of y, you keep as it is, differentiation of e raised to ax will become a times e raised to ax, and g of y is a constant, differentiation of e raised to minus ax will become minus a times e raised to ax. So which one I will rewrite it as here, dou z by dou x is equal to a times f of y e raised to ax minus a times g of y into e raised to minus ax. This is a partial differentiation of your equation number 1 with respect to x. Now you apply the value of dou z by dou x as a sin y is equal to a as it is, f of y as it is, replace x as 0 according to this, so it will become e raised to 0. Similarly a as it is here, g of y as it is, e raised to minus ax, x value is what here 0. So on simplification, from this you take a common, so a cancels, f of y minus g of y is nothing but what here, sin y. So which is going to be, so equation 2 and equation 3 you have to solve by using simultaneous. So f of y plus g of y equal to 0 is equation number 2, and f of y minus g of y is equal to sin y is equation number 3. So on simplification, so g of y cancels, f of y plus f of y is nothing but 2 times f of y is equal to 0 plus sin y is what here, sin y. On simplification, f of y is nothing but what here, sin y upon 2. So you replace this sine of y upon 2 in any equation 2 or equation 3. You will get the answer of g of y as minus times sine y upon 2. So this f of y of sine y by 2 plus and g of y of minus sine y upon 2, these values we got it. So applying equation number 1, we'll get sine of sine y upon 2 into e raised to ax minus sine y upon 2 into e raised to minus ax. See, I want to simplify this. This z is equal to sine y upon 2 into e raised to ax minus sine y upon 2 e raised to minus ax. So who is common here? Sine y upon 2 is a common. Sine y upon 2 is common. So what left here inside? E raised to ax minus e raised to minus ax. Or I can say that sine y as it is, 2 you push for this, e raised to ax minus e raised to minus ax upon 2. So this is nothing but a formula for what here? Sine y as it is. This is formula for sine hyperbolic of x. So I have written a is the sine hyperbolic of ax. So this is nothing but the result of the means sine hyperbolic of x in terms of exponent. So that simplification I have written directly. Okay. So in this way, so this kind of examples we are going to be solved for homogeneous and non-homogeneous. Next, based on this, we'll go for the next concept in the next class as using a linear partial differential equations.